Hello everyone and welcome to this course's last video. Thank you for following until now. This is a tutorial about Networkx, and today we are going to examine a dataset with Networkx. You will find this dataset later on GitHub so that you can play with it yourselves. It's a dataset about Quakers. You may be wondering now what those are. So think about societies. Societies existed long before social media for many centuries. Some were secret, some were open. Some of them even continue to exist today. This dataset is about a Quaker society, which dates back to the Middle Ages. The Quakers were Protestant Christians who separated from the Church of England and were founded in England in the middle of the 17th century. They supported religious tolerance on a broad scale, and as a result of that, they grew in their numbers a lot in the middle to late 17th century, and they spread throughout Britain, Europe, and the colonies in the New World, in the US, mostly in Pennsylvania, which was established actually by a Quaker's lead called William Penn. The data used in this tutorial is essentially a list of names and relationships among the Quakers of this early 17th century society, and it came about because scholars have long linked these Quakers' resilience and expansion to the strength of their network. So imagine that this society lasted for centuries. The Francis Bacon Project tries to rebuild early modern Britain societal networks, mainly from the 16th until the 18th century, and this is the source of this dataset. So we have in fact two files with which the dataset consists of. The early modern Quakers, the nodes, are listed in the Quakers node list CSV, so you can find it here. And what you have here is, oh, this is a mistake. Sorry about that. It's probably the name, yes. The name, the historical significance of this particular person, the gender, the birth date, the death date, and an ID. And then we have the relationships between those Quakers, the edges, which are listed in this Quakers edge list CSV. So here you have a source and a target. Let's now read the nodes from these files and see how we can build a graph out of this, because this is essentially what we're trying to do, right? So first of all, what I would like to do is obviously what we do every time, import the most important libraries, all the usual suspects, including this CSV now, because we're going to need it to actually read these CSV files. We're going to need this community because this is going to be used for community detection later on. And then just the usual libraries that we have. So the first thing we need to do is to read the nodes from the node list and then the edges from the edge list, and then append them to two separate lists. So this is what we're doing here, essentially. So I have already uploaded these two files in my Google Colab, so I don't need to upload them anymore. I just read them from there and then create these two lists. So if I run this piece of code, this is going to create those two lists. And let's see the length of this list. So let's see how big our graph is. So if I print these two lists length, there are 119 nodes and 174 edges. So this is not a huge graph. So in Networkx, what you can do is you can combine these lists into a single network object, and this object recognizes the relationships between nodes and edges automatically. And this kind of object is called a graph. And to begin with, what we need to do is to initialize this graph object with this following command that you see over here. So we just call it from Networkx library, this graph. But what you need to remember right now is that this graph object is empty in the beginning. So what we need to do is now to add the nodes and the edges data that we just read previously in those two lines from those two lists. And this is what we're doing here. And to get some basic information from the graph, we can print this graph. This is not a visualization. It will just give you a bit of information about the graph. And this is telling you that it has 119 nodes and 174 edges. And this is not a lot of information really about the graph. I mean, it's a bit of information, but it's not a lot. So what we would like to do really now is to also look maybe at the average degree of the graph, for instance, just to have an idea of the graph. So if we print the number of nodes again, edges, the average degree, and then maybe the content of the graph so that we can see a little bit how the graph structure looks like, right? So this is again the number of nodes, edges, and this is the average degree of the graph, which is not very high, I would say. And then this is the graph content, so you can go over it and check how things are represented here. But essentially, in this graph object, we want to have the entire network. So this is what it represents. So we have the nodes, we have the edges, which we have already added as pair of nodes to the graph. But a cool thing that Networkx does is that it allows us to attach additional information. So if you remember from the lecture that we had previously, the theoretical one, we had attributes for nodes and edges. So we can add these attributes. And why we need these attributes is because later we'll need to calculate different metrics. And we would like to put these attributes back into the graph structure because only in this way we can really analyze and see exactly what's happening in the network with that information. So we have to make sure that the attributes from the CSV file, then we include in the graph. So then if we go to this previous list that we have before to look at the attributes, essentially you remember that we created these lists from this kind of a file, right? So what we would like to do now maybe is to also get the attributes from there and add them to these nodes. But how shall we do that? Essentially, as you can see over here, it's not difficult to set the attributes. There is this function that has already the attributes, but we need to create some particular type of objects in order to do that, right? So if we look at these functions, these set node attributes and set edges attributes, they require the data to be in the form of a Python dictionary. And then in the dictionary, we have the keys, the node names, and then the values are the attributes that we want to assign. So what we need to create and what we're doing right here is to create this kind of dictionaries for each attribute specifically, and then we add them to the graph using the functions, right? So first of all, over here, we create these 5 empty dictionaries that you can see over here. These are dictionaries that correspond to all these columns over here because this is what we're trying to add to the nodes, right? We're in the node list. And after we do that, we can iterate through the node list and populate each dictionary with the corresponding items. And we're doing this over here. So if I run that and then running this as well, just to have it there. So we're doing this by knowing the positions or the indices of each attribute. So for instance, the historical significance is at index 1, the gender is at index 2, the birth is at index 3, and so on. And then after we have all of these, we created these dictionaries, and now they're ready to use, and we can add them as attributes to the nodes in the graph objects with these two functions, right? Set node attributes, and then we could also add set edges attributes, but we are looking at nodes now. So then now all nodes have these attributes that we were planning for them to have. And for instance, one thing we could do here is to display the birth years of the nodes just by iterating through them and then retrieving the birth year attribute. So the way we can do this is like this. And then if we print them, we see that we have the following nodes. So this is the name, Joseph Wyeth, which is born in 1663. Alexander Sheen of New Tile, born in 1621, and so on. So what we've learned so far, right, is to create this kind of a graph object. And now we look into different metrics, right, and use them. So the first one that comes to mind, and maybe the easiest, because you see how simple the code is right here, right, is this network density. So before calculating the density of the network, let's think about what we know about the data set. So we know that it has 119 nodes, 174 edges. The edges don't really carry any extra information, and also they're undirected, which suggests symmetric relationships between people, right? And you can see all the details about the nodes, like the attributes, the names, the historical significance, and so on. All these aspects influence how you handle the data set, because if you think about it, this data set, like I said before, also has a small number of nodes, relatively. I mean, we could also have a graph with millions of nodes. So if we think about that kind of a scale, then this is small. But if the dataset has a very large number of nodes, like millions, like I said, it would be more useful to work with subsets, for instance, or to use a supercomputer than to do visualizations. For datasets that are smaller like this, we can do visualizations. You will see immediately when we plot the graph as well that visualization, even for this dataset, it's not exactly very easy to see a lot of details. So this is why we can employ this kind of a metric like the density. And if we calculate it, then we notice that we have a network density of 0.0247. The density, if you remember, is on a scale from 0 to 1. And this number indicates a relatively sparse network, which matches what you will see in the visualization in a second, right? A density of 0, if you think about it, would mean that there's no connections between nodes in the graph. And then a density of 1 would mean a fully connected network with all the possible edges present. So if we look now of how the graph looks like, so the graph looks like this. So this is on the lower end of that range. So it's not extremely dense, but it's not, it has a few edges, right? It's not completely disconnected is what I wanted to say. So this is how the graph looks like. This is a little bit crowded, so you can't really see everything really well. So what you can do is to try to make the graph a little bit less crowded and then plot it based on the degree of the nodes. So the nodes with higher degrees would have higher circles that are representing them. So let's try and see how that works out. So now you can see it a little bit better. So we can see these people with like more influence, right? Like George Fox, like Margaret Fell, James Naylor, William Penn that we already talked about a little bit, George Whitehead, and so on. I'm not going to go through all of them now because we're going to have more metrics, and as you will see, these people will appear in many of these metrics. So now another thing that we could look into is into this shortest path calculation. This is a bit more complicated than the density because it determines the minimum number of nodes and edges that connect any two nodes, which can be difficult to identify in large network visualization. So this metric is really essential to trace this kind of indirect connections. For instance, like finding a mutual acquaintance between two people and so on. And then to calculate a shorter path, what we need to provide, so we have this Python function already in, or Networkx function in Networkx, shortest path. And what we need to provide is the entire graph, right? Our graph G, the source node, and the target node. So the path essentially of that you want to get. So if you want to find the shortest path between Margaret Fell and George Whitehead, right? Then you would put Margaret Fell as the source and then George Whitehead as the target. And then if you print the shortest path, then you see that the George Fox is a common between them, right? So depending on the size of the network, this might take some time because this is because what this function does is essentially it evaluates all possible paths before selecting the shortest one, right? So what this includes now, the results includes the source, the target, and then any node that is in between that. So this is the node in between those two. And I wanted to say this here. And then I wanted to say that this didn't take so long here because our graph is actually quite small. But if you do this for a very large graph, it might take a while until it calculates all the paths you can imagine. Fox, this Fox guy. So if we try to find it over here, George Fox, right? You can see already that this is a little bit of a hub because it has so many connections. And like I said, we have plotted this with the higher degree of connection it has, the bigger the bubble is. It's likely that we will encounter this person then in many other shortest paths if we calculate them. Uh, he was also one of the Quakers founders, so from a logical point of view, this is also is making sense because he had an important role within this society. Then there are many other metrics that we could have here. Now, if we print the length of that path, that's 2. But we could have also other metrics. So one classic example here is the diameter of a network. And that is defined as the longest of all the shortest paths. So once we calculate the shortest paths between every possible pair of nodes, then the diameter represents the distance between the two nodes that are most distant from each other. And what this metric does is it helps us understand the network's overall size and the maximum distance between the most separated nodes it has. So to get that diameter, all we have to do is call this function from Networkx that you will see over here, right? Diameter of G. And let's see what happens when we run that. We're getting this error. And why we're getting this error? Well, the answer is in this box. It says right here that found infinite path length because the graph is not connected. So we haven't talked about this yet. Um, so what we could do next is we could try for ourselves and see if the graph is really connected or not. We already know from the visualization before that it's not, because if you look here, it's clearly that this is one connected component, but this is not connected. And there is not only this, there are others as well, as you can see. I'm not gonna list all of them right now. But now let's compute at least the largest connected component and see how that looks like. So we could have a look at that. Um, so what we do here essentially, we see with this function, we see if the graph has more than one connected component. Um, if it does, then this will return false. And then we can use this kind of connected components function to get the list of all the components if it has more than one. And then we will use this max to get the largest of the connected components. And then what we could do afterwards is create a subgraph of this largest connected component that we can already see over here pretty much. Then from there, we can calculate the diameter of that connected component and then print its diameter. So let's do this. So yes, we have more than one because we got this false here, just like we assumed. And then the network diameter of the largest component is 8. This means that the longest shortest path between any two nodes in the network is 8. So unlike density, which ranges from 0 to 1, interpreting whether a diameter of 8 is large or small isn't that straightforward. Because for metrics like this, it's often best to compare the value to those of the networks with a smaller, similar size and structure. So this doesn't give you a lot of information, but it gives you a little bit of an idea. And this kind of structural analysis that we'll perform on this network, you can see it over here already, is this triadic closure, which shows you if two individuals both know a third person. So, because if this is happening, then they're likely to know each other as well. So, for example, like we had before, Fox knew both Fell and Whitehead, and then it makes it probable that also Fell and Whitehead knew each other. And this forms a sort of a triangle in a network with three edges connected, right? Fox, Fell, and Whitehead. And the number of these triangles in the network can help identify clusters, communities, and just individuals that are closely interconnected. Sometimes we will see later on as well in other measurements that we will have individuals that are linking two different communities that might themselves be separated otherwise. So now we have this. So how we measure this is through this transitivity function. This is also measured on a scale from 0 to 1. And in this network, we get this kind of a number, which is 0.169, right? This is noticeably higher than the density. And given that our graph is relatively sparse, there aren't many potential triangles in the first place. And this is why we might have somewhat higher transitivity than we would expect. But this means that the nodes with many connections are more likely to be part of these closed triangles. And to confirm this, normally you would gather more information about the nodes that have a higher number of connections. And how this transitivity is calculated, it's calculated essentially as the ratio of triangles over all possible triangles. So it shows the degree of connectivity of a graph as a ratio of actual connections to all possible connections. So this is very similar to density. So remember these two kind of metrics, density and transitivity. Um, and we also remember that both of these deal with possibilities, not with absolutes. So this is important to remember that you're essentially calculating a probability. So think about these numbers in that terms. And now let's take a look at centrality. So if we're looking at centrality, it's important to remember that once we have gathered some basic metrics about the overall structure of the network, the next step is to identify the most important nodes of the network. And this is what we're doing through centrality. Since there are different ways to define the importance of nodes, there are also multiple methods for calculating the centrality. And here we are going to look at three of the most common, which are degree centrality, betweenness centrality, and then eigenvector centrality. Now, this should have not been here, but we're clearing it out. Anyway, degree centrality is probably the simplest and most widely used method for key nodes identification. And I want you to remember that a node's degree is quite simply the number of edges it has. So this is very simple to calculate. So if a node has 10 other nodes it connects to, then its degree is 10. This makes degree centrality easy to understand because it's something that is very, very simple for us humans to imagine. Because it just represents the number of direct connections a node has. In a social network, nodes with the highest degree are those individuals who know most people. So these nodes are often called hubs, like I also mentioned earlier, and calculating the degree is the quickest way that you can do to identify them. Calculating centrality for each node in Networkx is more complex than the metrics for the entire network. It still requires only one simple line, command-like line, as you can see over here, right? So the centrality function that we're gonna generate here, generate dictionaries when the key is a node and the value is the centrality score. So in Networkx, this format is designed so that you can add these centrality measures back into the network as the node attributes, just like we added the other attributes earlier on. So in this part of the code over here, we're doing just that, right? We're creating this degree dictionary, and then like we just did before with the other dictionaries, and then we are setting it as node attributes. And that's it. Programmatically, this is very simple. So then if we want to check, for instance, George Fox's degree along with all the other information we have access to, based on this graph that we have created, then we can just print this. And then we can see the historical significance, it's his gender, the birth year, death year, the ID, and its degree, which is 22. Another thing we can do is to sort these nodes based on the degree centrality and then compare them directly by using this sorted function to arrange the dictionary by its keys or values. And in this way, we make it easy to identify the top nodes if we want to. So by creating this sorted degree with this sorting function and then printing top 20 nodes. Then we can see who has the highest, who has the second highest, and so on. But let's get back a little bit at this sorted degree, because this is a little bit more um, complicated function. If we look at these arguments, so the first argument is the dictionary you want to sort. This is clear, right? The second one specifies what you want to sort by. And this item getter of one means that you want to sort by the value of each dictionary entry. And then last one is reverse is true. That means that you want to have the nodes with the highest degree appear first in the list. So it's on a decreasing order of the nodes, right? As you can already see. Um, so degree centrality is really useful for learning about the largest hubs, like I said, but it's not really very useful about learning anything about the remaining nodes. So you're just left with that essentially. And for nets like the net we have here, you could see that from the visualization before, which are the highest hubs. So this is not a big surprise, which are the biggest hubs, because you could see over there already. They are centered among the founders mostly. So if you can see Fox, Fell, Penn, there's this Keith, Nyler, Curley, Barrow, and so on, right? So, okay. So this is not, I mean, it's important, but it doesn't give you a lot of information about everything else. So what you can calculate then, as you can see over here, we can calculate the betweenness and the eigenvector centrality. And then let's just look at the eigenvector centrality first. And the reason why we're looking at this first is because it builds on the concept of degree centrality that we just looked at. But it considers not just the number of nodes connections, but also the importance of its connected neighbors. So it evaluates both how well connected a node is and how well connected its neighbors are. And the decentrality also ranges from 0 to 1, with values closer to 1 indicating higher centrality, just like the others. And this metric is useful for identifying nodes that can quickly disseminate information to a large portion of the network. So, for instance, if you're connected to many influential individuals, you can spread the message very, very effectively. Everybody has used Google. So you've already encountered in your lives an application of eigenvector centrality. It's the PageRank algorithm, which is based on a similar concept to determine the ranking of web pages in search results. And we have seen this in itself. I mentioned it as an algorithm in the last lecture. And then this is how we run betweenness centrality. So this is programmatically, again, very simple. It's just this function and then the argument is the graph itself. And oh, I was looking at betweenness, but they're both the same pretty much. Programmatically speaking, you just the name and then G. But the betweenness centrality differs from the other centrality measures because it doesn't really focus on the number of connections the node has, but it analyzes all the shortest paths that pass through a particular node. If you remember this from the theoretical lecture on network analysis. And for this reason, it can take longer to compute than other centrality measures. Here, like I said, we have still a relatively small data set, so it's not that obvious. But have that in mind if you're gonna ever work with like 1,000,000 nodes. Betweenness centrality then is also measured on a scale from 0 to 1, And what is very good at is identifying nodes that serve as bridges between different parts of the network. So it provides, in a way, a quick way to identify nodes that are crucial, not because they have many connections, but because they link different groups. And this is very important. And then we can add it as attributes again to the graph. Um, we can get them sorted again, and then we can get this degree of centrality. We can notice that this betweenness centrality is also very similar to those nodes that have a high degree centrality, right? But not all of them. And if we compare these two, right, George Fox is there, William Penn is there, and so on and so forth. But if you compare these two lists, pretty much, um, we see in degreesness, in this betweenness centrality, two women, Elizabeth Levens and Mary Pennington, whose importance was not really captured by the other centrality. So Elizabeth Levens, Mary Pennington. Um, so if you want to identify nodes with high betweenness centrality but low degree, what you can do is you can sort these lists that we created earlier. And by this list here this suggests that these two women served a crucial role as intermediaries, right? Bridging the gap between different graph segments, which might be otherwise disconnected. And then sometimes you can also discover different things about the individuals that you know. So, um, now if we look at community detection next and modularity, finding out which communities or subgroups make up the greater social structure is another frequently asked question regarding a data set. And there are many ways of identifying communities and clusters within a network, but modularity is one of the most used approaches, I would say. It measures the relative density of connections within a network. So a community, also known as a module or a modularity class, has a high density of connections among its own nodes, but lower density with nodes outside its group. So this is what defines a community, more or less. Um, sorry. And this metric provides an overall score, which indicates how divided or fragmented the network is. And this can help to partition the network into distinct communities. So to do it, we can employ this function, greedy modularity communities, right? So we are calculating the communities. This method, what it does is identifies the optimal number of communities within the graph and groups all the nodes into subsets based on these communities. So unlike a centrality function, this method does not produce a dictionary, but generates another kind of object which is similar to a list. And it's essentially a set which is similar to a list, and each of these sets corresponds to a group and contains the name of the individuals within that group. So to add this information to the network, like we have done before, we first need to create a dictionary because you remember, in order to add the attribute, those functions needed a dictionary type. So we create a dictionary that assigns each person a numerical value which represents the group they belong to. And this is what we do. Oh, sorry. This is what we do over here, right? Um, And then to get a deeper understanding, what we can do is combine these measures and get deeper insights. For instance, we can identify the nodes with the highest eigenvector centrality within modularity class 0, for instance. And this is what we're doing over here. So then ranking nodes by eigenvector centrality provides insight into the key individuals within this modularity class. So as we can see here, we have these names, Naylor and Fell and Hogwheel and Farworth and Pearson. So these were also some notable Quakers as well. And finally, what we want to do is to find and list every modularity class and its members. Um, um, Sometimes we would like to do that, and we iterate essentially through all the communities. But if you see something unusual, it's this line over here. We're excluding modularity classes that have 2 or fewer nodes. And then from the visualization, you might recall that the nodes included many small components with only 2 nodes. So modularity identifies these small components as separate classes, obviously, because they aren't connected to the rest of the network. So by filtering them out, you gain a clearer understanding of the larger modularity within the main component of the network. So it separates all of these components, takes them away, and then you calculate the modularity here in this component, which is what you want to do, because the others are probably not so significant because they are not really even linked with the rest of the network. Then we notice that there are 7 classes there, right? 8 actually. 0 through 7. And if we go back to the connected components, what we could do is to list the connected components, right? We can try to make a list with the size of each of the components to see if there are others except for that one. And now maybe I want to print here all the components and then see. So yeah, there is one with 3, but there is the big one with 96. There's one with 3, but the majority of them have 2, so not many. And then if we plot a histogram of the component sizes, then we can notice over here that there aren't many. There is one with 96, then 3, and then the rest are with 2, right? Like about 10 of them. Then if we create a subgraph with the largest connected component and visualize it, that would be interesting to see. So this is how the largest connected component looks like. So now we eliminated all the others. This is the largest connected component. And what you can do now is export your graph in this format, right? In this Gephi format, essentially. After you have this kind of a file, then you can visualize it in Gephi. And with that, you can play a lot more with it. And then you can save it also in another kind of format as well. But this is one of the most common ones. This was the end of this Networkx tutorial. Thank you for listening, and have a nice end of the course. Bye.